Well, hello everyone. My name is Dave Cleland. I'm with MBSI WAV in Medicine Hat, Alberta, and welcome to another edition of Tech Talk with Dave. So today we're going to talk about broadband power systems in relation to how I would power my radios up the tower. One of the things about modern equipment is that they're starting to draw a lot more current, and we're going to have a session here in the near future that's going to talk about MIMO and its effect on how much power devices draw in the on the tower site, and we're going to talk about a number of things about antennas and that kind of stuff. Before that, though, we're going to talk about what makes up a power system. And while this is old hat to many people, so some of you that are new in the business, well, maybe you haven't thought about this quite this way in the past. So we're going to understand what the requirements of the devices in your system, whether we're going to convert from AC to DC, we're going to start at DC and remain there. Do we need standby battery or universal power system? Do we need PoE? And then finally, we're going to talk a little bit about, and maybe the driest part of this, although you're going to use it, I know you're going to use it eventually. You're going to learn how to size cables, and we're going to talk about the various ways that Ohm's law can be expressed and how this is going to work for you to figure out exactly what you need. All right. So what's your most valuable tool in power systems? It's the digital VOM. The voltmeter. Typically, they can measure DC or AC volts. They can measure DC amps and up to maybe 10 amps, from a few milliamps up to 10 amps. And they can measure resistance, again, between the plus and the COM port on there of short circuit, 0 ohms, right up to many mega ohms. How much they cost? All depends. I think every technician should own one. I think every technician should have a good one in their back pocket or in their toolkit. You can get them as inexpensively as tens of dollars, and you can get them as expensive up to thousands of dollars, depending on the accuracy and the features that you want in it. What does a field tech or an engineer, application engineer, need in accepting most systems and turning installing and turning them up? Well, some unit that's worth around $100 or a couple $100 will do 99% of all your measurements. And so generally, the units that are of that quality, they can be dropped. They can be they're reasonably waterproof, and you have yourself a piece of gear that's probably going to last your lifetime. The one I'm using at home in my lab, I've had for I don't know, 40 years, maybe 35 years, and it works just fine. As long as I keep the battery changed and don't let the battery run out and spill the acid out of the little 9-volt battery, everything's fine. All right, some helpful additions and attachments. It's good that if you have various probes, alligator clips, stake-on adapters, all sorts of things that you need to make your VOM more useful. And PoE test jigs, homemade or commercial. They're not that expensive. I have a commercial pair that I use all the time. But you can make them yourself if you want to do that. If you're handy with electronics and want to put together a little package, you can do that. So it adds more versatility to your meter. So calculate the power requirements of your devices. I always start off troubleshooting with a piece of paper. A piece of paper and a pencil, and I will take and make a drawing. I need to know what it is that I'm actually looking at. Lots of times I don't know what I'm looking at right at the beginning. If I sit down in front of a piece of gear and I start to look at the readings it may have on its display or whatever the case happens to be, I may not know what's all involved with that power that the unit is drawing. So I make up a schematic of my system. I find the power requirements in a spec sheet. One of the things that can happen in the in our telecommunications world is that something is not drawing enough power, meaning that there's a function that's broken in it, or something is drawing too much power, meaning that there's a short circuit or a near short circuit that's loading down the power supply. And it may be that your power supply is robust enough that it can actually run with that near short circuit on the power input of the device. So you need to know the specs of what's connected to your power supplies. You need to know the input voltages that are required. Of course, they're all 48. Is there 30 volts and 48 volts? PoE, is there what are the differences? Some equipment in the past operated on 24 volts. Some equipment, some mobile radio equipment, land mobile equipment can operate on 12 volts. And so there's all kinds of different requirements for the powering your devices. In the broadband world, typically we either use PoE or we use 48 volts at the tower site, and sometimes at the subscriber location, the SM might run on 30 volts. Now, for everyone that went to technical school, I'm sure this was a couple of months of theory that you had to take and work your way through. Ohm's law. Ohm's law is the description of how voltage, resistance, and current are all related to each other. Knowing any two factors of any of these equations on the wheel, on the Ohm's law's wheel here, will let us be able to calculate what the other factor or the other two factors are in determining how this particular circuit is behaving. For a long time when I was in the field, I had a copy of this wheel taped to the inside of the top of my toolbox, because it's oftentimes you need to take and recall this as you're troubleshooting, especially, and it was nice to have that confidence that you know that resistance is equal to voltage over current. For example, there at 330 on the wheel there. Or whatever the case happens to be, because sometimes the terms can get a little bit confusing and you can turn them around, like I squared over R equals P, or R equals P over I squared. Which one do you want to use, and that sort of thing. So anyway, have the wheel. This is I put it here so that you could take and copy that and use it when you need to. All right, from a slightly different perspective, here's the wheel expressed just slightly differently. So in the case here, we're solving for the inside, the P, I, V, or R, depending on what color it is, and those the three equations represent the formulas that work to solve for that particular variable. So in case we didn't know, I is always the indicator of current. R is always the indicator of resistance. And that can be measured in ohms, mega ohms, kilo ohms, all kinds of different values, but it's resistance. V equals voltage, and P, of course, equals power. So we have a typical system here. We've got a cabinet that's at the base of the tower, that's got the standby batteries in it, it's got the power supply in it. We're using 48 volts to power our devices up the tower, and I want to know where I need to measure what. All right, so here's kind of the measurement schematic of a typical site. So the measurements in red I use with power applied and the load attached, so that I can see what the voltage or the current happens to be at that particular location. So red is measuring current, yellow is measuring resistance. Resistance is always measured without the power connected, and voltage, of course, is the voltage across the positive and negative, whatever that happens to be. And depending on where you're measuring it, you might want the power on, so you're measuring a load voltage, or you might want it off, so you're measuring static voltage. One thing to remember, that on a system that isn't drawing any current, the voltage is going to be the same everywhere you measure it. So when the system draws current, then you see the resistance of the leads, you see the resistance of the connections, you see the effect of the current that the device is consuming from the power supply itself. So sometimes that's an easy fact to disregard. You want to measure voltage, and so maybe the device up the tower isn't connected yet. You measure 48 volts across the batteries, or 54 volts, or whatever it happens to be. Then you measure that across the surge protectors. You measure it everywhere, and it's because there's not any current flowing. When there's current flowing, you're going to see a different voltage. The battery and the power supply are going to be the highest, and then as you move away from the power supply up towards the devices up the tower, you're going to see the voltage drop caused by the current draw over the resistance of the cable. So, some of the tests that you need to do when you're first turning a system up or you're troubleshooting a system is that you measure the resistance of your DC power cable, whatever that happens to be, whether it's a separate cable or it's Cat5 cable. Doing PoE, you remove the power sources and the Ethernet terminations because they have resistance, so they're gonna affect what your ohm meter reads as you measure this. Then you put the ohm meter across the cable at one end or the other, usually the bottom end, and at the top end, your tower climber has got a little jig that you make up that you just plug on the end of the power cable or the end of the Cat5 cable that puts a short circuit across it, and then you can take and measure the resistance of the system that you're measuring. So typically, when you put a short circuit across the top, the resistance that you read is going to be 2 times the resistance going up and down, right? So if the resistance was 10 ohms going up and 10 ohms coming down, you would read 20 ohms at the base of at the VOM and know that half of the resistance is in the cable going up and half is in the resistance coming down. So from that, you go back to your ohms wheel, and you can actually figure out what the voltage drop is and that sort of thing. All right. Surge protectors. This is a big, let's say, question mark, a big magical device. Whether it's working or not, it's pretty easy to figure it out. So the pairs of any category 5 surge protector are going to be 1, 2, 3, and 6, 4 and 5, and 7 and 8. That's the normal TIA 568 cabling that we do to put the connectors on the cable, and how the pairs in the cable are connected together. So pins on the line should have 0 ohms resistance to the complementary pin on the equipment jack, right? You need a short circuit. You should have a short circuit. Anything measuring from one pair to another pair should have infinite resistance. There should be no connection, no DC connection from, let's say, from pins 1 and 2 to pins 3 and 6. Should be wide open. All pins should have infinite resistance to ground. If the device has suffered from a surge and either the multiple oxide varistor has broken down or the gas tube has been fired, there will be resistance then between the pair and ground that you're measuring. So between maybe lead 1 and ground, there's a gas tube there and going across. And if I have resistance between pins 1 or 2 and ground, then I know that this device has taken a hit at once upon a time, and that should be replaced. I don't know of any current surge protectors where I could take and replace the MOVs, or I could take and replace the gas tubes, although you could. There's nothing saying you can't, because it's just components mounted on a circuit board. But generally these devices are pretty inexpensive, and the surge protectors themselves. And so replacing the surge protector after some kind of incident, storm, or whatever the case happens to be might be easier than replacing the components in them. But that's totally up to you. Calculating the size of cable that we need to power our devices. A little bit more complicated, but essentially all cables have a particular resistance, right? And it's measured in spec sheets as maybe ohms per 100 feet or whatever it happens to be. And so when you know the maximum current that you need to supply up to your devices at the top of the tower, then you know you can figure out, using Ohm's wheel again, you can figure out what the resistance that you can allow yourself in that, and then from that you can take and pick the size of conductor that has the maximum current rating that will support your device, or has the resistance that's low enough that will support your allowed voltage drop on the device. And you can take and oftentimes DC cable is just positive and negative, two conductor, but you can take and reduce the gauge size that you require by going to 4 conductors. And I thought that out of the scope of this presentation, calculation of resistance in parallel, but needless to say, by doubling up my cabling, I can reduce the resistance by 4 times. So into a quarter of what it is. So that's a common method of increasing the amount of power that you can deliver up to the top. Cat 5 PoE uses that all the time for high-powered PoE, such as what the Cambium's 450M in 5 gigahertz requires. Then we're using all 4 pairs to provide the power. So we have actually 4 conductors that are passing the positive and 4 conductors that are passing the negative. Now that was just a brief introduction. If you have any more questions, or you want any more details, or you need any help with the calculation, feel free to contact us at MBSIWAV.com. Any feedback or comments on Tech Talk, you can send to marketing@MBSIWAV.com. And any new topic suggestions, please forward them. And we'll be happy to have a look. And who knows, maybe the next Tech Talk is going to be your suggestion. Bye for now.